Okay, so we need to prove the following theorem. It was formulated last time, but we didn't prove it. So the theorem says a connection HE on a fiber bundle E over X is flat if and only if we have flat section locally. So for every X from X and then P from the fiber, there exists an open neighborhood of X and section of the restriction of E to U such that S of X is P and it's flat. So nabla S is 0. Okay, so let's prove it. So if part, so connection, right, so if part is this direction, so let's prove this direction. So if I have a flat section for each P, then my connection is flat. All right. So we take all this stuff as in here. So take what X, P, S, U as above. Then I claim that S, so S of U is an inverse submanifold of E. Submanifold of E.
Well, basically, S is the inclusion, which is injective immersion, right? So just
by definition. All right. Then I'm going to use that. So first observation: if I take any y from U, then I can consider the tangent space at S of y to S of U. So first of all, I claim that it is inside H S of y E. This is just because the section is flat.
So basically, if I consider the ds, right, which sends me a vector from the base to the vector at the point P, then this condition says that it is in horizontal direction, right? So therefore, this is just is an implication of this thing. So because nabla S is 0. On the other hand, dimensions of these two guys, they just match. Right? So actually I know that a pi composed with S is ID, right? So therefore, from this it follows that d pi composed with ds is ID. So therefore, ds should have rank which is equal to the dimension of X. Right. But this means that, well, ds, the rank of the ds is the dimension of this guy, right? And the dimension of this is also X, right? Because I have a pi which maps from TE to TX, right? And pi restricted to H is an isomorphism, right? So, so I have that dimension of T S of Y as U is X, and also dimension of H S of Y S of U is, sorry, dimension of X here should be, right? Dimension of X, and this is also dimension of X. So this means that actually T S Y S U equals to the horizontal, to the fiber of the horizontal bundle S Y E. All right, then so let me take two vector fields, psi and eta. So these are vector fields on E. So take this. Then of course H of psi, H of eta, this belong to H, gamma of H of E. Just by definition of what is H. All right. But also I can take, so since this is true, I can restrict it, both of them to, well, to S of U, right? And this will be like the corresponding, this will be vector field on S of U then, right? It could, you know, at each point the tangent vector could look somewhere like not in the tangent direction of S of U, but because of this and because of this, this is really, restriction is really a vector field on S of U, right? And the same for this. So these are vector fields of S of U. Right. And so we actually can take now and compute so remember my omega h was, so what we're trying to prove is that this guy is 0. It was minus k of, well, so let me maybe just start with reminding what is. So, right, so just a reminder, omega h was negative k, and then, so omega h of psi eta is this guy. So my goal is to check whether this is zero. And k is the projection along HE to VE, to the vertical bundle. Right? So I need to take commutator. Of these two things. So let me restrict it to S of u. Right? But then it can be checked maybe in coordinate wise that this is computing this commutator is the same as computing the corresponding vector fields on SU. So h of psi, h of eta, and so need to restrict. So this commutator behaves well with respect to restrictions. That's what I mean.
It was just from homework.
Maybe, but maybe you can link it to homework, but I'm not sure. But it is, you just need to see that, okay, if I'm computing right, so basically what can happen is that, well, when I commute, right, in coordinates, I could take a derivative in a direction which is not HE. That would be a difference between commutator of this and commutator. So here you will never have derivative not in a tangent direction to SU. And here you might have, right? So you first commute and then take a restriction. But since these are horizontal, you never, so these are already tangent to SU, right? So since they're horizontal, you don't have this derivative. So basically, this is a short explanation like this. Or you just, sit and do it in coordinates. So you'll have horizontal coordinates, vertical coordinates, and compute first this and then this. And you see that this is just the same thing. All right? But if I commute two vector fields of some manifold, I get another vector field of this manifold, right? So this is actually inside vector fields of S of U. But I know that at each point, this gives me a vector from HE. Right? Because, well, at each point this is an element in here, but I know that I have this equality. Right? This basically says that h of psi, I commute with h of eta, so I restrict it to S of u. So basically, I can evaluate it now at a point which is in S of u, which is my point P.
for example. Right, so remember I had this x, and then in the fiber of x I had p, I had s, which is this s, such that s of x was p. So p is inside s of u. Right, so if I take p, this will be one of the values of this guy. So this is my p. And I know that then this belongs, because this is in the vector field of S of u, I restrict it to p, so this will be inside here. Well, here I will have s of x, right? Which is like just p. So this is inside Cp S of u, and this is inside Hp E. So my conclusion is that this is really a horizontal thing. But then if I take k of h of psi, h of eta, so since it's horizontal, then it's so like this. Then its vertical component is just 0. Right? So this is just 0. And we proved this direction. So everything is just because S of u is a submanifold. And the commutator of two vector fields of a submanifold gives me another vector field of the same submanifold. And that's the main reason why all this works. The other direction is harder, but we will skip hard part, just name it, which is Frobenius theorem. So next is this one. So this direction. So we suppose that omega h is 0. Just basically 0. Then if I take two sections of the horizontal bundle, right, and I compute their commutator, this will be inside. This will be inside also. This will be also a section of horizontal. Right, because the vertical component is 0. Right. So we will use this observation, but also Frobenius Frobenius integrability theorem, or just Frobenius theorem. Okay, which is like that. So let M be a smooth manifold, and D, it's a subset, first of all, Tm, but also it's a vector subbundle. So vector subbundle. Also, vector subbundle of Tm is called distribution. And also we need some additional condition for it. Suppose, suppose what we say is that D is a Lie algebra,
right? It's closed under commutator. That's the thing that we have actually here, right? So suppose that for any psi and eta from the gamma of D, we have the commutator is also inside gamma of D. Then, okay, in words, the theorem says D is locally integrable. And so locally integrable. That is. So what does that mean?
For any x from M, there exists submanifold N of M, which contains this point well, such that for any y in N, T y N is dy. Dy is a fiber of D at the top of the point. Right, so that's this is a theorem. Okay, we skip proof of theorem. It's mostly calculus, but it just naturally arises when we talk about curvatures. Anyways, so let's just use it. So we're proving that there exists flat section,
And we're using that actually horizontal bundle is an integrable distribution of TE, of E.
So by Frobenius theorem, HE is integrable, is locally integrable. And so let N be submanifold of E. So this is submanifold of E such that well, it contains the point P. Well, we fixed the point P, right? So we're proving this theorem. So we say that okay, omega h is 0, right? Then for any x, P, there exists S, blah blah blah. So x and P are fixed, right? So P, I want this point P that I fixed to be inside N. And T, well, for any Q, from N, TQN is just HQE. So this is for any Q from N. So just this is just our N from Frobenius theorem for HE. All right. Then so recall that so we have have pi, right, which is the projection of e to x, and if I take just by the definition of HE, if I have dB prime restricted to HPE, so this is just the isomorphism. Actually, this is for any point P, so maybe don't even, so P is some fixed point, so maybe here, let me write Q. So this is isomorphism for any Q from actually E. So this means that actually pi well, restricted to n, right? So H, Q, E are tangent spaces to n, right? And this is an isomorphism from tangent space to n to tangent space of x, right? dq pi. So therefore, if I take pi restricted to n, this will be local. This will be a local diffeomorphism. So I can invert it locally, right? So there exists some n tilde. It's open in n. I'm just rewriting what does it mean for it to be local diffeom. Open in n, and u open in x. Also, I would like my point P to be in here, such that pi restricted to n tilde, so it's from n tilde to u, so this is diffeom. So I can consider inverse of it. So basically then S, so we are constructing S. So the S then will be inverse of this guy. So S will go from U to N tilde. So P restricted to N tilde inverse. So take. Then just by construction S of X is P. Right, because, well, if I take, so this is just inverse of pi, right? And pi of P was X. So pi of P was X, S is an inverse of pi, so S of X is P. So this condition is satisfied. Also, we need to check that this is flat section. So also, number of S is 0. Well, this is kind of clear because just by construction, all tangent spaces of N tilde, they're horizontal. And so the ds works like that. It takes some vector space on X and lifts it to the some vector from the tangent space of X, and leaves it to a vector in N tilde. So tangent to N tilde. And the tangent space to N tilde is horizontal every time. Right? So therefore, the lift by S is horizontal. This actually means this. Right? Our definition was that nabla basically SV was the vertical
vertical projection of the push forward of V. So that was our definition of number V of S. Go back to the notes of previous lecture. And so this guy is actually, so this is inside. So this is a section of, if my S is like that, this is a section of T and tilde, right? Which is the same as section of H E restricted to N tilde. But since it's HE projection in the vertical direction, will just give me 0. So therefore, this is just 0. And we're done. So we have a flat section. All right. So this is it. So this is a very important theorem, which has like a lot of good corollary. So you just can rephrase in a lot of ways what does it mean that you have flat connection, right? So for example, then from the homework problems, it means that like along small loops, you have parallel translation, which is identity, or it's the same as saying that section is locally trivial if you have a vector bundle. It's also another similar problem, and all that just follows from the application of Frobenius theorem to this definition for curvature for Ehresmann connection. So this is like a handy generalization. Also, but maybe you saw another definition of curvature, which was not like that, but rather like for vector bundles. So if my E is a vector bundle, I can actually define the following tensor. Well, just a notation, right? So if I have V and W, these are vector fields on X, and suppose, well, I have E, which is vector bundle, and suppose that I have HE, which is linear connection, in the sense that we discussed last time, which means that I actually have this nabla in the old sense, a final linear connection. All right? So affine connection. And suppose that for every VW, let me just introduce this notation. So R of VW is just nabla V, nabla W minus nabla W, nabla V, and minus this V minus the number of commutators, sorry, number of commutators, minus number of commutators. So this is a map from, so R VW, for each VW, so this is a map from sections on E to sections on right?
but you can also apply it to some section, right? So this will be. So what I want to say is that actually this is like this map, which is our linear map. Obviously, you can check that this is actually a tensor. So it is actually C infinity of x linear. You just can check it by hands. The same way as for torsion. Right, so I'm claiming that R so this will be important for this. So V, W, and S. So this is multi linear over C infinity of x. So it's like a so this is a tensor in this sense. All right. So this is more familiar maybe for some of you notion of curvature. And let us just relate this guy with the curvature that we had for Ehresmann connection. So theory says that for any V and W, so these are from vector fields. So these are two vector fields on X. Section S of E and point X in my base manifold X. We have the following relation. So if we take this R of V, W, S and evaluate it to point X, so this will be some point in E, right? So I'm claiming that this can be computed as follows. I take V horizontally lifted to a vector field on E and W horizontally lifted to a vector field on E as well, and compute omega H of it. And this will be, and then evaluate it at the point S of X. So now let's just check that all this makes sense, right? That the object on the left-hand side is the same as object on the right-hand side. Or maybe we need to do some identification to understand that. Okay, so first of all, what is VH and WH, right? Okay, so VH is just defined as its horizontal lift of a vector which is given. So it's just horizontal lift, like point-wise horizontal lift of V. So VH of P is just by definition horizontal lift at a point P to a point P of V pi of P. So where we have this, then okay, so on the left hand side I have what? So this leaves, so this is a section of E, right, and evaluated at the point. So this is actually belongs to EX fiber, which is like vector space. Okay, this guy, omega H. So I take
two vector fields on E, compute the curvature of it, and this will be so curvature computes the commutator. So this is again a vector field on E, right? But at the end, and then I evaluate it, right? So this will be, so when I evaluate it, the right hand side, so this will be in T S of X E, right? But actually I can say better, since omega H, the last operator there is K. So this will be actually, I can replace this with V, right? So, but actually, omega is K, and then of something, right? So we have this. So right hand side is inside V S of X E. Still not quite, right? So I have E of X and V S X of E. But these are the same things because my E is vector bundle, and fiber is just a vector space, which corresponds to the vertical, the fiber of the vertical bundle. Okay, and so this makes sense. All right, so that's the connection between these two. Well, to prove this it will be kind of tricky, but it's also, I think, interesting. So proof. Let's prove it. All right. So for that, I will need the following observation. So suppose that nabla, so let nabla be a linear connection on E. Well, at the end of the day, we will apply this not to E that we started with in theorem, but some other vector bundle. But okay, hopefully this will be clear. I don't want to make more letters for vector bundles. So suppose that I have some linear connection, nabla. So I'm saying that, well, nabla is, as we defined, it was mapped from gamma of E to gamma of T star X tensor E, like that. Right, so if we don't specify argument here, so this part is like a vector field. But we can generalize it actually. So this is like a D, but on the degree 0 of the RAM complex, right? So it's like a D, like it's a generalization of D on the degree 0 of the RAM complex. So I can multiply this by C infinity of X and apply D. This will give me one forms, right? But I can generalize it to nabla, which actually is from sections on K forms, so which is lambda K T star X tensor E. And then it maps it to gamma to one evaluated E forms of 1 degree higher, which is lambda K plus 1 T star X. This is just given by the following formula. So if I have nabla
just given by Leibniz rule, really. So if I have nabla and I apply it to form tensor section, so I'm just saying that this by definition should be d omega tensor s plus minus 1 to the power k omega wedge nabla s. So wedge means that I wedge it with this part of nabla s. Well, with this part. Nabla s is evaluated at one form, right? So so omega is k form. So this is k plus 1 then form. So this is k form, but I need to wedge it with another one form here. There's k plus 1 form. So this is k plus 1 form, well, tensor. So this is just the definition. Really. So you just start with this nabla and then by Leibniz rule extend it to such a map. That's one thing. And so we have the following. So if I have some lambda, so I don't know. This is usually so take lambda, which is from gamma of t star x tensor e. Then we have the following claim, which I will not prove because we proved the same thing for d, and here it's just proved again in coordinates. And since this generalization of d, it's not surprising that it should be like that. So if I take lambda, apply nabla to it, and then so this will give me, this will be a two form related in E, right? So it is two vector fields VW. Then this will be nabla V. So it is two vectors, right? And this therefore this gives me a section in E. So this is related already. This is a section. So this will be nabla V of lambda of W minus nabla W lambda of V, and then minus lambda of the commutator. So it's familiar formula if you replace nabla with D. And so just generalization of this. Okay, so I'm going to use this. Apply to one particular connection, but okay, this connection will be so okay. That's one thing. To what connection and to what vector bundle I'm going to apply this formula. So okay, so I have going back. So I have nabla. This is my connection on E that I started with in my theorem. And then I would like to introduce what's called pullback connection, nabla tilde. So this will be a connection on another vector bundle, which is VE. VE, as we know, it's a vector bundle over E. All right.
Okay, so how do we define? So that's pullback with respect to what? With respect to pi. So we have actually this picture is over x vector bundle, and then pi is this map. So we pull back. So we pull back vector bundle E to E itself, and this will be pi star of E. So pi star of E is here, but the pi star of E is actually the same as VE. So fibers of pi star of E is the same as VE. So therefore I wrote it like that. Okay, and so yeah, I have pullback bundle, and I have nabla, which is connection on E. So nabla is here, and well, but I want to have nabla tilde, which is on this vector bundle. How do I define it? So that is nabla tilde is a unique connection satisfying the following. So if I take nabla of S so I have nabla tilde. I would like to apply it to the pullback of the section S with respect to pi, and also at some vector field V. Well, this is actually I can relate it at a point x, right? Well, here it should be not x, but rather some p, which is, since it's all going on at the top of p, so this should be p. So I can actually, so this is a tangent vector at TPE, right? So I can relate nabla at d pi p of v, and then put it in a point x, where x is pi of p. Right. So that's the defining relation for nabla tilde. So basically, what I'm saying is that for nabla you have Christoffel symbols in some local basis for gamma of E, and in some local basis for Tx. So you just pull back this basis to E. You can just take this basis and pull it back to this. This will give you local basis on VE and local basis of the cotangent bundle of your section, and then you just say my Christoffel symbols in this pullback basis is just the same. That's how you define nabla tilde. Okay. Okay. Does it make sense what I'm saying, or people completely shut off? So you just need to ask questions if not.
How would you see is there's a pullback of the bundle along the same bundle is the vertical subbundle?
Yeah, so let's see. So pullback means that I take EX, but I know that EX is just isomorphic to
VXE. Well, EX is isomorphic to V, not X here, but again, we're using the fact that it is linear, and so each fiber is a vector space. So tangent bundle to fiber is the same as this fiber itself. So that's what is used here. And fibers of pi star X are those guys, and fibers of VE are, well, I didn't write. So P. So here P, pi pi of P is X here. So that's why. And then, well, I'm just doing the most natural. So okay, I have a connection in here. So how on earth I can get connection on this guy? So I'm just doing the most natural thing, right? I'm just saying, okay, I want the Christoffel sinus balls just be the same in some fixed. So I fix the basis here, and I obtain some natural local basis in here just by pulling it back here and saying, okay, in this pullback basis, just Christoffel symbols are the same. This exactly will be what I wrote here.
And can we find a horizontal distribution in this bundle? Or this?
For Nabo tilde, we always can define horizontal distribution. We can go, so we know how to go from the linear Riemann connection to usual connection, right? And so you're asking how to go from like if you have a linear connection, how you can define a Riemann connection, right? So basically you are just doing the following thing. I wanted to say that, but you just take a point X, take point P, which is at the top of X, and then consider all the curves through X in the base, and then you lift it. So then you consider the curve which are parallel to X in here. If you have connection, you know what is a curve which is parallel to this guy, and then you consider all the curves in the base, and consider all the curves here which are parallel to X. And consider all the tangent bundles, all the tangent vectors at P. This will give you some vector space, which will be exactly your horizontal bundle. So you take all the curves. I don't know, maybe there's a better way to say that, but that's how I know how to say that. So you take all the curves here, you consider all the curves in E, going through some fixed point at the top of X, which are parallel with respect to this gamma, right? Well, there's only curve. If you fix this curve, there's only one curve which is parallel to that, right? But then I vary gamma and see what are the tangent vectors at P at all the parallel curves that I have at the top. And this will be exactly my HE. So I don't know, maybe this is gamma 1, and then I have like some gamma 2, and so here I have gamma 2 tilde, which gives me like this vector here, and this gives me HPE, sorry. All right. So okay. Well, suppose we believe that now we have this Nabo tilde. This is on VE. All right. And I need to apply it. So now this is I need. So this will be my Nabo in this claim, and I'm applying this to some lambda. All right. Well, what would be my lambda in this case? I'm saying that it will be my map K. Where should I go? So K was the map from where to where? From this to this, right? It is just projection, right? And it is actually, since it's a projection, it's a C infinity E linear. Just this is an easy statement that it's C infinity E linear. Just follows from its definition. So therefore, so this is C infinity E linear. So therefore, I can think of it as a section of T star E tensor VE. So I know that if it's C infinity linear, then, sorry, it's not phi, it's just gamma of this. Right, Oleg, so at which point did you just shut off?
Just from.
But okay, so I just want everybody to be to follow. Otherwise, what's the point? Let me rather just maybe repeat. From which point should I repeat? Okay, so we have this guy. So I'm thinking of this map as just a section of this. I have nabla tilde, which is a connection on VE. Well, so you see here I have VE. And also I have, so my lambda is K now. My E is VE, X is E, so I have T star E, tensor VE. And so I'm applying nabla tilde. So I'm, in this relation, I take nabla to be nabla tilde, E to be VE, X to be E, and lambda to be K. And then I get the following. I get the following. So I already consider some lifts. So okay, let me just write this. Nabla tilde K. So it hits two vectors which I would like to be already horizontal lifts of something from X. This is, by this claim, it is just nabla tilde VH of K of WH minus nabla tilde WH K of VH and minus K of the commutator VH with WH. Right. So on the right hand side, I already have what looks like the curvature, right? And that's the main point. So I'm proving what? I'm proving. So let's see. I think it was on this. No, was that on this board? Maybe not. Yeah, it was on this board. Yeah, so I'm proving this. So the idea is to apply this guy, and so I have two terms here. So I can choose actually. So since it is R is a tensor, I can actually choose different fields which behave differently.
For some fields, these terms will be gone, and I will end up with just this relation, which is just omega. And for the other terms, this will be gone, and this will be the terms that will be in my expression, and this will be my R. Okay, so anyways, so we are proving. So let me go back to here. So I have this relation. Anyways, so let me see. So I have, I'm saying that, okay, it's clear that this guy is just a 0. Because it's k applied to something horizontal, right? In this, for the same reason, this is 0. So on the right-hand side, I already have, and h applied to this is just nothing. Well, h applied to vh is vh. Just h just does nothing to vh or wh, right? So therefore, what's written on the right-hand side is just omega h of vh wh. And that's exactly the right-hand side of what we're going to need to prove. All right. So now, what about the left-hand side? The left-hand side. So we need these guys, but we need to evaluate it at s of x. So I need nabla tilde of nabla tilde k vh wh. And so, well, this is a section. Well, this I can evaluate at the point s of x. So the question, what is this guy? Okay, so I'm going to use that this really is linear, C infinity E linear. So therefore I can choose some other vector fields which at this point s of x, they coincide with VH, WH, but actually as a vector fields, they're different than these guys. So basically, well, let me choose some coordinates y1, blah, 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 yn plus r. So let this be a coordinate around P, which is S, my S of x, right? This S that I fixed. Well, this is point P already. So n is dimension of x, r is rank of E. So therefore coordinates I have n plus r coordinates in E. Okay. Also we can assume that the first two coordinates give me tangent vectors corresponding to VH and WH at this point. So I can choose first two vectors of my basis just as I like, right? So I can choose it. I choose them like that. So d over dy1 at point P is just VH at point P, and d over dy2 at P is WH. So this is some vector field which is on E, which is different from VH. But why I'm doing this is because the commutator of d over dy's will be 0. This will make my life easier. So that's the whole point. So I'm replacing VH and WH with these guys, really. And also I'm saying that the first
n of them, this gives a basis in the horizontal direction. And the rest of them, they just complete this to the basis of TPE. All right. Okay. And so, right. I know that I can find so this guys, they just commute, right? So therefore there is it gives me integral distribution, right? So therefore so there is this integral submanifold corresponding to these guys. So let n be integral manifold of d over dy1, blah blah blah, d over dyn. Well, so here actually I need to restrict it to p, but I can, these are coordinates, so I can release this restriction, and I say that okay, they commute because these are d over dy's they commute. So therefore, by Frobenius integrability theorem, there exists some integral locally, some integral manifold of those guys, right? And well, also I would like it to be small enough such that pi n to u is just in the same logic as the proof of the previous, of the first theorem of today's lecture. So this is diffu. All right. And then I'm taking S tilde. So here, I'm kind of modifying S. So I'm taking S somehow, but then I'm modifying it so that it gives me an integral manifold with some given by vector fields of this sort, right? This is just some technical thing. So I have S tilde. I just define it to be pi restricted to n inverse. And this is from U to, well, to E. One last thing that I need to define is, okay, so I define d over dx right. So what I want is some coordinates on x, right? So therefore, well, I want this. I want some coordinates on x. So y's are coordinates on at the top, but I want some coordinates on u, right? Such that actually d over dx I is just this. So it just push forward with respect to this guy of d over dy i's. Well, this is just, well, I guess I'm just defining x I to be this. So I'm taking, well, xi of some point x, well, of some point x. So I'm just defining coordinates xi. So xi at some point x means that I need to consider pi n inverse of x lifted there and consider coordinate yi. So this is how I define coordinates xi. And then this will be vector fields on x. Okay, so I'm almost there. So, okay, what we need to compute? We need to compute this guy, right? So let me rewrite it. So nabla tilde of k of vh with wh of s of x. So I am saying, okay, s of x is just p, but these guys I just can replace them by d over dy1, d over dy2, since this is C infinity of E linear. So I'm saying that this is nabla tilde k of d over dy1, well, at point P, d over dy2. And then at point P. Okay, so then I continue. And I'm applying this claim, one more time. This one. But now I have different vector fields, as I said. So first time these terms were gone. This time I have d over dy's, which will give me this term gone. Okay, and this will give me left-hand side. So where am I? I'm here. So now I'm applying the same claim once again. So I have nabla tilde d over dy1 k of d over dy2 minus nabla tilde of d over dy2 k of d over dy1. And that's it. Because the commutator of dy1 and dy2 is 0. Да, здесь не коммутатор, правильно. Just like that. All right. And that's it, because the commutator of dy1 and dy2 is 0. Right, so the third term is in this claim is gone. Right. Now I need to go back through all the definitions to get the standard R that I started with. So first of all, I know that this happens, but actually this is S tilde is pi n inverse, right? So therefore, actually d over dyi is the push forward of d over dx I with respect to S tilde. This is just because of this and because of this, right? So I take this, substitute in here. So when I substitute, I will get something like k of S star tilde d over dxi. But look, this is the same as pi star of nabla of d over dxi s tilde. This is just from the definition of the covariant derivative. So what I'm saying is that, okay, what is the covariant derivative of S tilde? Well, I just need to apply S tilde star to d over dxi, right? and then take the the projection to the vertical direction. And then, and then I need to apply, basically, but then so this will be still in different in different vector spaces to identify them. Well, I need this also pi star here. So I just go back to the definition of nabla if I'm given HE. So this will be exactly the definition, right? So I push forward d over dxi with respect to a star and project to the vertical direction. Okay, but also, so I have this. So this I can replace with this. That's one thing. But also I have the definition of nabla tilde, which I don't know, I don't remember at which, maybe not here, on this board. So nabla tilde satisfies this. So you see pi star here. So pi star makes nabla tilde to be just nabla. Remember that, just from this definition. So therefore, when I substitute this into here, right, I have nabla tilde d over dy1 of pi star of this. Right, so, okay, so I just substitute, I get nabla tilde of d over dy1 of pi star of nabla d over dxi s tilde, minus similar term. But this guy now becomes, from the definition of nabla, tilde, it just becomes nabla of d over dx. So here, not j, but 2, right? So here I have 2. d over dx1 applied to nabla d over dx2, and then applied to s tilde, and then minus the same term, but with 1 and 2 interchanged. Right? So this is what this guy, so I continue. So finally, I just claim that this is just the same as R of d over dx1, d over dx2 applied to s tilde. Right? Because, the commutator term is just gone because the commutator of dx1 and dx2 is 0. And then I just apply this to s tilde. But this is all C infinity of whatever. This is of x, C infinity of x, and in this entry C infinity of e linear. Right? So therefore, I can replace this. So d over dx1 at my point x is just the same as v, and d over dx2 at my point x is just w, and s tilde at point p is just, not at point p, at x. It is just the same as s of x. At point p, nothing changed. I just changed s to s tilde outside of this point p. All right, and so this because at points the values of all these vectors, they just coincide, and all this is C infinity of corresponding manifold linear. I can just replace this with d over dx1 with v, this with w, and here, this is at the point x, right? So, and S tilde with S. And we're done. Again, the main idea is to use this relation for Nabla, this claim, basically 2 times. But each time you're choosing different vector fields, but at a point of interest they coincide. Outside of point, they are different, so and different terms in this claim vanish. That's the main thing. Also, this justifies the minus sign, because you see the minus sign appears here. This are gone, and so we defined omega to be minus this. So this is justification of minus sign. All right. I'm done torturing.
А вы говорили уже, когда экзамен будет?
Ну, не, я не говорил. Вообще по расписанию официально 30-го. Ну, в принципе, в сессию там еще есть один вторник, который 23-го, который чего-то рановато, мне кажется. Наверное, я даже не буду всех в один день. Я, наверное, возьму там 3 дня и просто люди запишутся там вот на протяжении 3 дней, в какой из дней им удобно. Но там ближе к 30-му, конечно. Я обычно так делаю, и так работаю. Хорошо.
30 что-то поздно.
Ну, 30 это чего за день недели?
Вторник.
Вторник? А, вторник тоже, да.
Устный будет?
Ну, да.
То есть вы даете билет?
Ну да, стандартно. Ну, я заранее вышлю все вопросы. Прям вот какие вопросы в списке будут, такие будут.
То есть 30-го
Последний.
еще теория будет экзамен, и придется сюда прийти.
Ну, скорее всего, нет. Это вторник, да, но сюда за понедельник вы тоже не очень хотите приходить, 29-го, да?
Ну, было бы славно.
Ну, я, наверное, сделал так. Я сделал как-нибудь так. Четверг, пятницу на предыдущей неделе будет возможность. И, допустим, 30-го. Вот, 3 дня вот таких будет. Я там сделал какую-нибудь Google табличку, чтобы люди записывались, когда кто хочет прийти. Ну, там заодно будет видно, где толпа набирается, чтобы если у кого была как бы, возможность распределиться в другой день. Ну, понимаете, если толпа, то это как бы может растянуться на долго.